In this video, we're going to find a method to find the slope of the tangent. And we're going to start by looking at rate of change. So the first thing that we look at is what is rate of change? Well, rate of change is a measure of how one variable changes with respect to another variable. For example, speed is a rate of change because it measures the change in distance with respect to a change in time. In math, we discuss the rate of change of y, which is our dependent variable, with respect to x, which is our independent variable. Change in y over the change in x, so delta y over delta x, is called slope. What does the rate of change look like for various parent functions? Well, if we look at the linear function, we can see that the delta y over delta x is constant. Rather, the slope is constant, and therefore the rate of change is also constant. Now, how do we find the slope of a curved function like the quadratic function? Well, slope is just basically, if we draw these tangent lines at any point, we can see that the slope of the curve changes as we go from left to right along the x-axis. So what we see right here is we see that the slope is variable. Therefore, the rate of change depends on x or is a function of x. So the slope of the quadratic function is a function of x. It changes as we go from left to right. We can see the same thing with the radical function. Okay, so the radical function has changing slope as we proceed from left to right, from x is equal to 0 to x is equal to infinity. Again, the slope is variable. Therefore, the rate of change depends on x or is a function of x. So what is our conclusion? Our conclusion is that linear functions have a constant rate of change, whereas nonlinear functions have a variable rate of change, and therefore their rate of change depends on x or is a function of x. So the first rate of change that we'll look at is the average rate of change, also known as AROC or AROC. The rate of change is constantly changing in the graph to the right because the slope of the graph is constantly changing, right? We can see that the slope goes towards 0 right here. If we draw a tangent line right there, the slope is 0. So it goes here. Sorry, that's not a good one, but you can see that several tangent lines would lead to here, and then it just goes towards 0, and now it starts to go this way. Okay, so we can see that in fact that the slope is changing as we proceed along the x values. The average rate of change between the 2 points is just simply the slope of the line connecting these 2 points, and such a line is called a secant because it cuts through those 2 points. So it's simply just y2 minus y1 over x2 minus x1, where y2 and x2 are or x2 y2 is 1 point and x1 y1 is another point. So let's take a look right here. It says determine the average rate of change between 1 and 7 on the x-axis. So literally I'm going to go to 1 right here, okay, and I put a dot here, okay, and then 7 on the x-axis, and I put a dot here, all right, and I have my 2 points now. My points are 1, -6, and my other point here is 7 and 2, and essentially, I'm going to draw a line between those 2 points and find the slope of that line. Okay, so I've drawn my line there, and now I can do the slope. And so the slope of the secant is simply equal to y2 minus y1 over x2 minus x1. Okay, I'll choose this second point as my x2, y2. So I'm going to go do 2 minus -6 right there, over 7 minus 1. And I get 8 over 6. So the slope is equal to 4 over 3. Moving to the next page, it says, what are the intervals for which the average rate of change is positive, negative, and for what values is the average rate of change equal to 0? So if we look at this right here, which portions of the graph have a positive rate of change, or that means a positive, again, this just means a positive slope, all right? And a positive slope means that we are progressing from quadrant 3 to quadrant 1. That's when you have a positive slope. A negative rate of change is just the opposite. That's quadrant 2 to quadrant 4, represents a negative rise over run or negative slope. And rate of change is equal to 0. That's when we have our turning points. So take a second, look at the graph and see if you can figure out for yourself when we have positive rates of change, negative rates of change, and over what x values or on what x values do we have rate of change equal to 0. Okay, so positive rates of change would be on the intervals from x goes to infinity to -4, right? As you can see right here, we've got a positive slope. Then we have again a positive slope as we go from 2 to infinity. Notice that we use round brackets around -4 and around 2 because right at -4 and right at 2 we have a turning point or where the rate of change is equal to 0. And so that's where we write that. Now, negative rate of change is when we have a negative slope, and that's on the interval from -4 to 2. Okay, so we've talked about average rates of change. Now let's take a look at instantaneous rates of change, also known as IROC. While the average rate of change looks at an average change in the function's values over a range of x values, the instantaneous rate of change looks at the rate of change just at one point. The instantaneous rate of change is the slope of the curve at that one point right there. Therefore, the slope of the tangent. And recall that a tangent is a line that passes through the curve at that point and has the slope of the curve right at that point. So that's a tangent line right there. We approximate the slope of the tangent as follows. We can create a secant line that goes from x to another value, x plus h, but we make this h value so small that basically we're calculating a secant that is so small that it basically looks like a tangent. This simulates a tangent line since the secant becomes nearly parallel to the actual tangent with a very small h value. So again, we're going to pick a point here and then we're going to add a very small value of h to that point and make a secant that is essentially approximately a tangent. So the formula for instantaneous rate of change is given as f at x plus h minus f at x over h. Now you might be wondering, why is it just h? Well, again, we're going to take, this is just slope, right? So we're just going to take f at x plus h, which is going to be my y2 value, that's my y2 value, minus my y1 value, which is right here, that's my f at x. Scroll up here so you can see, so that's my y2 and that's my y1. So f at x is my y1 all over x2, and this is my x2 right here, this x plus h, minus x. So you can see why we're just left with h in the denominator here in the formula for instantaneous rate of change, because the x's will cancel and we are left with only h in the denominator. So the next question right here says, estimate the instantaneous rate of change at 2 seconds given this function for the height of a toy rocket. So we're going to find it at 2 seconds and we're going to find the instantaneous rate of change. So we're going to take a very small h value. So what I mean by a small h value, if we are approximating it, we say that h is equal to 0.001. So the slope of the tangent is going to be f at x plus 0.001, we make our h very small, minus f at x all over f at, h, which is just 0.001, my h value right there. So what we can do is we have our x value, it's 2. So what I'll do is I'll find f at 2.001, okay, and so I'll insert 2.001 into the equation, and then I'm going to find the value of the function at just 2. Okay, so putting the 2.001 into the height function, I get 140.46, so 140.46, and I'm going to subtract that with 140.4, and now I'm going to divide that by the h value, which is 0.001, and I get 60 meters per second. All right, and again, this is all going to be approximate, right? Because essentially what I'm doing is I'm still using a secant where h is very, very small. That's why this is like an approximate instantaneous rate of change. So the slope of a tangent, developing the concept of a limit, it's not very satisfying to approximate the instantaneous rate of change. So in this lesson, we'll find the exact value. So let's keep scrolling down over here. We're going to find the slope of a line tangent to the curve y is equal to x squared at this point p 3, 9. So I want to find the slope of that tangent. So what I'm going to do is I'm going to go h units to the right, and I'm going to place another point here. And this is my point Q. And if I'm going h units to the right, then my x value is 3 plus h. And my y value, if my y value is equal to x squared, and my x value is 3 plus h, well then my y value should just be 3 plus h all squared. All right, so that's my point Q by going a little bit h units to the right. So we'll draw a secant here. So I'll insert a secant. Okay, there we go. I've drawn a secant right here. Okay, and then write an expression for the slope of this secant if slope is y2 minus y1, x2 minus x1. Okay, so we'll write this right here. Slope of the secant is equal to y2, so that's 3 plus h all squared, minus y1, which is 9, all over x2, which is 3 plus h, minus x1, which is just 3. Note that we can simplify the denominator, and then this is simply 3 plus h squared minus 9 all over h. So does the slope of this secant represent the slope of the curve at point P? Well, not yet. So it does not. And only if h goes towards 0, if the distance between P and Q goes towards 0, will I get the slope of the tangent. So only if h goes towards 0 will we be able to calculate slope of the tangent. So where would we have to move Q in order to make this the slope of the tangent? Well, Q would have to approach, Q would have to get infinitely close to P. We have to take Q and move that infinitely close to P so that we are able to get a tangent. In this GIF that we see here, we have a different curve, and we have a point Q and a point P. We can see that that forms a secant, but as Q gets infinitely close to P, the secant becomes a tangent. So I'll press play here, and you can see that happen. Right? As Q goes towards P, the secant becomes a tangent. So as Q infinitely approaches P, the secant becomes a tangent, and that means that H has to approach 0 infinitely. If q gets infinitely close to p, then we must introduce the concept of a limit. The limit is when a variable infinitely approaches a value. In this case, q will infinitely approach p when h infinitely approaches 0, when the distance between q goes towards 0. So the slope of this function right here, remember, if my q was at 3 plus h, 3 plus h all squared, then my slope is going to be the limit as h approaches 0 of 3 plus h squared minus 9 all over h. So what we can see there is we can see that we can calculate the slope now using the idea of a limit, right? We have this secant, but now we're going to make h go towards 0. Now you may notice that how can we have h going towards 0 if h is in the denominator? So as we will see in future examples, using some algebraic techniques, we can manage to get rid of h in the denominator and actually evaluate what the slope of this tangent is without having to divide by 0 and produce an undefined quantity. So here we go. The definition of the slope of a tangent, the exact instantaneous rate, is given as the limit as h approaches 0 of f at a plus h minus f at a all over h. And we have a little diagram there that, again, is essentially what you saw with q and p, now using actual just variables. Okay, let's move on to the first example. In this example, we're going to find the slope of the tangent to the function f at x is equal to 2x squared plus 3 at x is equal to 2. I'm going to approach this by, I'm going to first find the slope as a function of x. So I'm going to wait, and I'm not going to substitute x is equal to 2 until the end. So the first thing that I'm going to do is I'm going to say, all right, well, the limit or the slope of the tangent is equal to the limit as h approaches 0 of f at x plus h minus f at x all over h. And let's do a little bit of work on the side. Well, if f at x is equal to 2x squared plus 3, if now my argument is f at x plus h, well, I'll plug in x plus h where x is. Okay, so there we go. This is my f at x plus h, and that's my f at x, and my h I just keep the same. So I'm going to write over here limit as h approaches 0, and now I'm going to sub in my f at x plus h. So 2x plus h all squared plus 3 minus f at x bracket 2x squared plus 3 all over h. I keep going, limit as h approaches 0. I'll expand this bracket, so this is x squared plus 2xh plus h squared plus 3. And now what I'm going to do is I'm going to distribute this negative into the bracket. And I get minus 2x squared minus 3 all over h. Okay, in my next line, I'll take this 2 and I'll expand that into the bracket. So I will get the limit as h approaches 0 of 2x squared plus 4xh plus 2h squared plus 3 minus 2x squared minus 3 all over h. And looking at my numerator, I can see that there are several terms that will subtract to 0. So 2x squared minus 2x squared, that subtracts to 0. Plus 3 minus 3, that's going to subtract to 0. So let's clean that up in the numerator. And we'll write the limit as h approaches 0 of, and I'll just put this right, I'll do 2h squared plus 4xh all over h. So again, still can't evaluate the limit yet because I have h in the denominator, But those of you might have seen that, okay, well, if I have an h in this term and an h in this term, plus I have a 2 and a 4, I think I can factor out some common factors. So in the numerator, I'm going to factor out 2h, and I'll get h plus 2x all over h. Now you'll see that I have 2h times this bracket divided by h, which allows me to now cancel out these h's, and I will have the limit as h approaches 0 of 2h plus 2x. And at this point, I can now say, well, yes, if h goes towards 0, this term right here, this h right here, will go towards 0. So this is, now I actually can substitute 0 over here and say, okay, well then 0 plus 2x is equal to 4x. So my therefore statement will be the slope of the tangent is equal to 4x. And writing it this way is saying this is slope is dependent on my x value. Slope as a function of x. So slope is dependent on x. And then I will simply sub x is equal to 2. So the slope of the tangent is equal to 8. In the next example, we're being asked to find the equation of the tangent to the function f at x is equal to 3 over x minus 4 at x is equal to 2. And in this case right here, I am going to directly substitute x is equal to 2 in the limit. So this is an alternative, right? In this example above, I first found slope as a function of x and then subbed x is equal to 2. But in this case right here, I'm going to directly substitute x is equal to 2 into the limit. So I'm going to say directly sub into the limit. Okay, so the first thing I'm going to do, if I need to find the equation of the tangent, an equation of the line, to find the equation of the line, I need slope and a point. So let's first find the slope, since that's what we're focusing on in this lesson. So the slope of the tangent is equal to the limit as h approaches 0 of f at x plus h minus f at x all over h. Now, in this case right here, I'm going to say f at 2. I'll just do some work on the side here. I'll put it in green, why not? F at 2 is equal to 3 over 2 minus 4. So f at 2 is just equal to negative 3 over 2. And then I have to do x plus h. So f at 2 plus h is equal to 3, and then 2 plus h minus 4. All right, so this should equal to 3 over h minus 2. Okay, so going back to this equation right here, so I'm going to have my f at x plus h, so limit as h approaches 0, f at x plus h is equal to 3 over h minus 2 minus f at x, which is just negative 3 over 2. And now instead of dividing everything by h, I'm just going to say I'm going to take this right here, this expression, that's the numerator, and I'm going to multiply it by 1 over h, because dividing by h is the same thing as multiplying by 1 over h. All right, so let's clean this up. I get 3 over h minus 2 plus 3 over 2 times 1 over h. And from here, I can see that I don't have a common denominator. So that means I'm going to have to take this one right here, and I'm going to have to multiply it by 2 over 2. And this term I'll multiply by h minus 2 over h minus 2. So here we go. I get 3 over h minus 2, and I'm going to multiply that by 2 over 2. And then this one over here, I'm going to multiply by h minus 2 over h minus 2. And 1 over h. Okay, so I go ahead and I figure out my numerators here. So my numerator is 2 times 3, well that's 6, okay? And then this is going to be plus 3 times h and 3 times negative 2, so plus 3h minus 6 all over, and the denominator here is going to be 2 and then h minus 2. Still 1 over h. Again, cannot evaluate this limit just yet because I have h in the denominator. So I move on, and I get 3h over 2h minus 2 times 1 over h. And so now we can see, oh well, these h's will cancel, and I'll be left with the limit as h approaches 0 of 3 over 2h minus 2. And so I can now directly substitute that as 0, so I get negative 3 over 4. All right, so now I have the slope. The slope is equal to negative 3 over 4. I have an x value. My x value is 2, and my y value is going to be negative 3 over 2. Right? I sub in the 2 to find the point. So now I have slope. I have a point, okay? And you can use point-slope form on a line. So that's this version right here, point-slope form. So the general y minus a y value that you have, so this one right here, is equal to slope x minus an x value that you have right there. So let's sub this in, y minus y1, so negative 3 over 2 is equal to negative 3 over 4 x minus 2. Right, let me clean this up. And we get negative 3 over 4x, and then this would become plus 3 over 2. And so we get y is equal to negative 3 over 4x. So this right here represents the equation of the tangent line. We were able to get the slope using limits. We found a point by substituting the given value, x is equal to 2, substituting that into the function and getting our y value, and then using point-slope form to arrive at the equation of the tangent line. All right, let's move on to the final question. This is an example of a thinking question. Find the coordinates x, y on the curve f at x is equal to 3x squared plus 2, where the tangent line is parallel to the line y is equal to 6x. Okay, so we have a line here, y is equal to 6x, and we have to think about our slope-intercept form, so y is equal to mx plus b. All right, so this line right here, we can see the slope of this line is equal to 6. But I want to find the coordinates where the tangent is parallel to this line. Well, we have to recall that if two lines are parallel, then their slopes are equal. So if the tangent line is parallel to this line right here, then I already have the slope of the tangent. So I'll say, therefore, slope of the tangent is equal to 6. And now I can go ahead and use my tangent line formula. So 6 will therefore be equal to the limit as h approaches 0 of f at x plus h minus f at x all over h, and I can start substituting some values in here. So f at x plus h, well, that's just the same thing as 3x plus h all squared plus 2 minus bracket 3x squared plus 2 all over h. 6 is equal to the limit as h approaches 0 of 3, expanding this out, plus 2 minus 3x squared minus 2. Again, that is a result of distributing the negative 1 coefficient into that binomial, all over h. 6 is equal to the limit as h approaches 0, 3x squared plus 6xh plus 3h squared plus 2 minus 3x squared minus 2 all over h. Looking for terms that cancel, 3x squareds cancels, the 2's cancel, Okay, and so I'm left with 6 is equal to the limit as h approaches 0, and I'll write 3h squared plus 6xh all over h. Looking at the numerator, I can factor out a 3h. All right, and then this allows me to cancel my h's. And I have 3h plus 2x. I no longer have an h in the denominator, so I can directly substitute the h in as 0. So 6 is equal to 0 plus 2x. So 6 is equal to 6x, and therefore x is equal to 1. If I have x is equal to 1, then I can just again substitute that into the equation. So therefore, my y value is going to be 1 squared plus 2, my y value is going to be 5, so the point is 1, 5. Okay, so again, we started by looking at slopes of the secant, or the average rate of change. Okay, and again, a secant is just a line that cuts through 2 points and uses slope formula. Then we approximated the instantaneous rate of change by using a small h value, and then we found the exact rate of change by using a limit as h approaches 0. Thanks for watching.